Hi, this is Bart. Welcome to the video for the EE40-43 Summer 2009 project. So the goal of this project is to design a robot which moves forward. If it hits something, it moves backward, turns around, and goes in a different direction. So here we have a working prototype designed by one of the TAs, David. So I'm going to turn the robot on. You can see it keeps moving forward. Something moves backward, turns around, goes in a different direction, and it keeps repeating that behavior. Now I'm going to talk about the different stages in actually completing the project. So how do you finish the project? By going through the project checkpoints. Unlike the labs, the idea behind the project checkpoints is that you first do your design or calculations on paper, get it checked off by the TA, then do the actual implementation and the debugging. So the project checkpoints are basically understanding the power supplies, the motor interface, which is probably the most difficult part of the project, the switch interface, and of course you also have to write the microcontroller code which ties all this in together, and we're going to be covering that in this video because the microcontroller code is pretty simple. You'll be given canned routines which you can use to make the robot accomplish the task. So first thing are the power supplies. Now in your lab 6 you use the microcontroller with the 3-volt power supply provided by 2 AA batteries. Now, so with the motor, you're going to be using a separate 4.8 volt supply, which is provided by a 4.8 volt, 2.3 amp hour nickel metal hydride battery, which is this one. Now, a note about the nickel metal hydride battery: it's got a lot of current capability. So, which means, as you know, you shouldn't short any battery, but especially with this nickel metal hydride battery, if you short it, chances are it'll get really warm and may even melt. So, one recommendation which the TAs will ask you to do is that to design everything and test using the benchtop power supply. Then, when the time comes for the robot to be mobile, you use these batteries. So, why do you need 2 separate power supplies? The idea is isolation. So, basically, when you scope the motor line, when it's running, you will see a lot of spikes on the oscilloscope screen, and these spikes are not good for a digital system like the microcontroller. So the idea is you use 2 power supplies connected by a common ground to ensure proper operation. So that's for the power supply part of the project. Now coming to the motor interface, so as you saw from the running robot, the idea behind the project is to have the robot move forward, and when it hits the switch, the robot moves backwards. So you'd like the motor to be controlled by the microcontroller. So the first design you could come up with is this one, where the motor is directly connected to a digital pin on the microcontroller, let's say digital 10. So as you know, logic 1 on the microcontroller is mapped to 3 volts, and logic 0 is mapped to 0 volts, but there are 2 problems with this design. The first obvious problem is that this doesn't provide the power supply isolation we just spoke of. The second problem is that the microcontroller cannot provide enough current to drive the motor, so this design is no good. So the next design you can come up with is this one, using a transistor like the IRF510 used in the boost converter lab. So the idea is that you connect the digital port D10 to the gate of the transistor. So when this becomes a logic 1, the transistor turns on, but since the digital port is connected to the gate, you draw very little current. All the motor current is provided by the drain source current. So this design might work, but there are 2 problems with this design. One problem is the IRF510 has a very high threshold voltage of 2 volts. So for a logic 1 value of 3 volts, it doesn't turn completely on. That's one problem. The second problem is with this design, you can only turn on and off the motor. You can't make the motor go backwards. So this design is also no good. So the third design is that you use a motor driver chip, which is the SN754410, as it says in your lab guide. Here, I'll go through a block diagram view of what the SN754410 does. Of course, you should read the data sheet for further information. So the SN, as I would like to abbreviate it, is a quadruple half H bridge driver. That means it's got 2 H bridges in it for driving 2 motors. So what's an H bridge? This is again a block diagram of what an H bridge looks like. As you can see why it's called as an H bridge, because it looks like an H. So the idea is, if you turn on transistors M1 and M2, the motor goes one way. If you turn on transistors M3 and M4, for instance, the motor goes the other way. Now, of course, you should not turn on transistors M1 and M4 or M3 and M2 at the same time, because then you will short VCC to ground. So that's why we provided a chip. This chip has inbuilt protection to ensure that doesn't happen. It also uses bipolar junction transistors. Here I've illustrated with FETs, but for your purposes, this block diagram would suffice to illustrate how the chip works. Now, the problem though is with this chip is that this chip is a transistor logic chip, in the sense that it understands, so it's a TTL chip. So this means that a logic 1 for the chip is approximately 4.8 volts and above. It's actually 4.5 volts and above. That means that you cannot directly hook up the microcontroller to this chip, because the microcontroller logic 1 is 3 volts. So what you need to design, like it says in your project guide, is a level shifter, which basically what that means is the output's 0 volts when the microcontroller sends in 0, so 0 gets mapped to 0, but 3 volts gets mapped to 4.8. Again, highly recommended that you do the design and debugging in stages. And if you have any questions, ask your GSI. So that's the motor driver part of the project, the motor interface. The third part of the project is the switch interface, which is very simple, in the sense that the switches you have are normally closed, normally open switches, which means, let's say the switch is not hit, the common terminal is connected to normally closed, and the normally open terminal is disconnected. If the switch is hit, the common terminal gets connected to normally open, the normally closed terminal is disconnected. You should use the multimeter to understand, you could use the multimeter to understand how the switch works, That's it for the project. Again, do all the designs in stages, ask your TA when necessary, be careful and be safe.